There is no recent event in space and astronomy that comes close in hype to the launch of the James Webb Space Telescope. After a wait that seemed like an eternity and tortured people in the scientific community, the new and powerful Space Telescope has made its way to its location, where it will use its large lens to capture mind-blowing images of the universe. Some of the pictures will be of the much-acclaimed Big Bang, giving scientists their best chance ever to understand the great event that started it all. However, why do we need to understand the Big Bang, and how will the James Webb Space Telescope help us do that? Join us as we dive into the terrifying pictures that the James Webb Space Telescope will take and how it changes everything. For decades, the leading space telescope in the scientific circle was the Hubble. Perched on its orbit around the Earth, it has taken stunning pictures of the universe, allowing scientists to reach many conclusions about the universe. However, a new space telescope is set to replace it as the leading space observatory. The telescope is the James Webb Space Telescope, or JWST. After a launch that basically was a gamble on the $10 billion telescope late last year because of the complexities, the JWST is now settled in place and can commence scientific or research work. It has undergone lots of configuration and fine-tuning. It will see the universe in the infrared, which is light at longer wavelengths than your eyes can see. Thanks to this, the JWST can look deeper into the universe than its predecessor and, as a consequence, detect events occurring further back in time, more than 13.5 billion years ago. But that is not all the JWST will do, because astronomers will also use it to study the atmosphere of planets in our Milky Way galaxy in the hope that signs of life can be detected. The JWST will function for about 2 decades, based on estimates of the amount of fuel remaining on board. NASA has not devised a way to refuel the JWST, so when the fuel runs out, it means the end of the mission. It is so far away that even sending a crew in for repair is not a possibility. One of the theories of the origin of the universe is the steady state. The theory was first proposed by Sir James Jeans in the 1920s, but it got a boost in 1948 when it was kind of reworked by Fred Hoyle, Thomas Gold, and Herman Bondi. Steady-state theory tried to explain evidence that the universe was expanding while still maintaining that the universe always looks the same and is therefore unchanging in practice and has no beginning and no end. How did the steady-state theory come about? The first clear example of an unchanging universe being argued in the context of astronomy and cosmology was in Isaac Newton's Mathematical Principles of Natural Philosophy, published in the 17th century. In Newton's magnum opus, he posited that the universe beyond the solar system was an empty space extending uniformly in all directions to immeasurable distances. He further explained through mathematical proofs and observations that all motion and dynamics in this system were explained through the single principle of universal gravitation. Hundreds of years later, Einstein formulated the theory of general relativity, and the early analysis showed that it created a universe that was unstable because it was expanding and contracting. Prior to this time, it was believed that the universe was static. In addition, Einstein introduced a term into his general relativity field equations called the cosmological constant. This constant was what held the universe steady, or in a static state. However, when Edwin Hubble, who the Hubble Space Telescope is named after, discovered that distant galaxies were actually expanding away from the Earth in all directions, scientists, including Einstein, realized that the universe wasn't static, which caused the cosmological constant to be dropped and the term was removed. Part of the reasons Hoyle promoted the steady-state theory was one mistake made by Hubble. When the astronomer was calculating the age of the universe using light from distant galaxies, he made an error and arrived at 1.8 billion years. This was far lower than estimates of the ages of the Earth and solar system made by geologists, which were billions of years. The issue now became how to answer the question of how the Earth could be younger than the rock inside it. But Hoyle's bigger reason for opposing the theory was religion. As a vocally anti-religion person, he was not comfortable that the Big Bang theory seemingly was close to the biblical account of creation. So Hoyle would rather entertain the idea that matter and radiation were continually created throughout the universe in just such a way as to keep the density and temperature constant as the universe expands, as inexplicable as that sounded. However, the credibility of the steady-state theory grew thinner as new astronomical evidence was detected. For instance, some features of distant galaxies weren't seen in nearer galaxies. This would make sense from the point of view of the Big Bang theory, where the distant galaxies actually represent younger galaxies and nearer galaxies are older, but the steady-state theory has no real way to account for this difference. In fact, it's precisely the sort of difference that the theory was designed to avoid. The straw that broke the camel's back for the steady-state theory was the discovery of the cosmological microwave background radiation, which had been predicted as part of the Big Bang theory, but was impossible to exist within the steady-state theory. This allowed the Big Bang theory to take center stage in the scientific discourse of the beginning of the universe. Another theory about the origin of the universe is that everything came from a black hole. Are you wondering how that could be true, since black holes only swallow things and never let anything that has crossed the event horizon come out? Well, the theory suggests that the whole universe is the inside of a massive black hole. Does that make you uncomfortable? However, the bigger problem of the black hole origin theory is that there is no way to confirm or even falsify the theory because it's impossible to cross the event horizon alive, so we default to the Big Bang theory again. There is also the plasma or electric universe theory competing with the Big Bang theory. In the electric universe model, gravity is relegated in favor of plasma and electromagnetism. The theory says plasma takes up an integral role in cosmological events and the fundamental order of the universe. It proposes that electric currents that flow along plasma filaments can shape and power galaxies. These currents stream into stars, powering them like fluorescent bulbs and prompting the births of planets. The electric universe theory was put forward by Nobel-winning physicist Hans Alfvén in the 1930s. Alfvén argued that if plasma pervaded the universe, it could carry electric currents capable of generating a galactic magnetic field. However, scientists have not been able to find evidence for the electric universe theory. The theory is not even technically a theory because it doesn't meet the National Academy of Sciences definition of theory. This is because it has no predictive power in the empirical world of natural events, with which we could witness physical signs of its presence. For most of human history, observers of the sky assumed it was eternal and unchanging, until Edwin Hubble dealt this theory an experimental blow in the 1920s. His observations showed both that galaxies outside the Milky Way existed and that their light appeared stretched, a sign that they were rushing away from Earth. Georges Lemaitre, a contemporary Belgian physicist, interpreted data from Hubble and others as evidence of an expanding universe, a possibility permitted by Einstein's recently published field equations of general relativity. Thinking backward, Lemaitre inferred that today's separating galaxies must have started out together in what he called the primeval atom. Interestingly, the first public use of the term Big Bang for Lemaitre's idea actually came from a critic, the English astronomer Fred Hoyle. In 1949, Hoyle coined the phrase during a defense of his preferred theory of an eternal universe that created matter to cancel out the dilution of expansion. Hoyle said the notion that all matter of the universe was created in one Big Bang at a particular time in the remote past was irrational. Hoyle would later deny intentionally inventing a slanderous name, but the moniker stuck, much to the frustration of some. But why is the Big Bang important and worth sending a multi-billion-dollar telescope to deep space? Well, the Big Bang theory is the leading explanation for how the universe began. Simply put, it says the universe as we know it started with an infinitely hot and dense single point that inflated and stretched, first at unimaginable speeds and then at a more measurable rate. And over the next 13.8 billion years, it has been expanding to become the cosmos that we know today. The JWST is already proving its mettle with the first batch of working images. NASA promised it would deliver the pictures, and they have arrived right time. While it's capable of taking stunning pictures of the universe, the most amazing thing is the speed with which it works. Images that would have taken the Hubble weeks to generate, the JWST can accomplish in a matter of hours. This is a big boost for scientists and researchers, as it will save their time and they will get the results faster. For example, the stunning picture of the SMACS 0723 that took only about half a day to be completed. The image actually contains some of the faintest objects in space ever captured. SMACS 0723 is a huge cluster of galaxies, and the method by which it makes it possible to picture the galaxies behind it is known as gravitational lensing. This means the mass of the cluster bends and magnifies the light of objects that are much further away from it. The red arc-like objects in the picture are lights coming from distant galaxies that have taken over 13 billion years to reach us. The JWST has also taken a picture of the Southern Ring, or 8-burst nebula. This object is a giant expanding sphere of gas and dust that's been lit up by a dying star in the center. When stars age, the way they make energy and eject their outer layers changes. However, when a star becomes very hot again, it energizes all that material it had previously spurned. The Southern Ring is huge, measuring about half a light year in diameter. Its location is somewhere about 2,000 light years from us. Of course, the JWST will help us see how stars are born, but it will also help us to observe how they die. Another picture in the first batch is the Stephan's Quintet, which is even farther away than the Southern Ring, at about 290 million light-years away. Stephan's Quintet is found in the constellation Pegasus and is notable for being the first compact galaxy group ever discovered. 4 out of the 5 galaxies contained in the quintet are locked in a cosmic tussle of repeated close encounters. Looking at the comparison between the image generated by the JWST and Hubble, you might not notice much difference. However, in the hands of the astronomers, they will be able to pick out different features that they would study thanks to the JWST's infrared sensitivity. The last of the first set of working photos from the JWST is the Carina Nebula, which Hubble has pictured before. Carina is one of the brightest nebulae in the sky, even though it's located about 7,600 light-years away. The interesting thing about nebulae is that they are like hatcheries where stars are born. Thanks to the superior ability of the JWST, we can now see more details of the Carina Nebula. The JWST is now set for action, and scientists will use it to stare back at the Big Bang. Because we can't see it directly, scientists have been trying to figure out how to see the Big Bang through other measures. In one case, cosmologists are pressing rewind to reach the first instant after the Big Bang by simulating 4,000 versions of the current universe on a massive supercomputer. It's like trying to guess a baby photo of our universe from the latest picture. The chemical elements of life today were first produced in the first generation of stars after the Big Bang. We are here today because of them, so the first stars must have influenced our own history, beginning with stirring up everything and producing the other chemical elements besides hydrogen and helium. So if we really want to know where our atoms came from and how the little planet Earth came to be capable of supporting life, we need to measure what happened at the beginning. You can call the JWST a time machine because in astronomy, the farther away things are, the older they are. That is simply because light from faraway places takes a very long time to travel to Earth. That means photos taken by the Hubble are not only a snapshot of space, but also contain the history of our universe. The captured galaxies appear to us as they were billions of years ago. What the JWST will do is take that time frame and go even further, allowing us to see farther back in time. Meanwhile, even though widely accepted, the Big Bang Theory has its criticisms, which you might want to know about. One of the most common criticisms is that it violates the first law of thermodynamics, which says it's impossible to create or destroy matter or energy. Critics claim that the Big Bang Theory implies the universe started out of nothing. However, proponents of the Big Bang Theory say that such criticism is unwarranted. The Big Bang doesn't address the creation of the universe, but rather the evolution of it. The other reason is that since the laws of science break down as you approach the creation of the universe, there's no reason to believe the first law of thermodynamics would apply. Another criticism is that the formation of stars and galaxies violates the law of entropy, which suggests systems of change become less organized over time. However, if you view the early universe as completely homogeneous and isotropic, then the current universe shows signs of obeying the law of entropy. Another point brought up by opposers of the Big Bang Theory point out that the early inflationary period of the Big Bang appears to violate the rule that nothing can travel faster than the speed of light. However, Big Bang supporters counter with some ideas. One is that at the start of the Big Bang, the theory of relativity didn't apply. As a result, there was no issue with traveling faster than the speed of light. Another related response is that space itself can expand faster than the speed of light, as space falls outside the domain of the theory of gravity. With the JWST, astronomers like Casey will be able to see so far back that they'll potentially spot the very first stars and galaxies. Hubble has seen light dating to about 400 million years after the Big Bang, which took about 13.3 billion years to reach us. but JWST has the capability to take us to 250 million years after the Big Bang. Does the 150 million years gap make any difference? It sure does. It's like the difference between seeing the first stars that ever turned on and arriving a bit too late after the funeral. This period in time when the first starlight shone through the universe is known as the cosmic dawn. With the JWST, humanity will be able to glimpse at it for the very first time. Beyond that are barriers. Prior to the first starlight, the universe was shrouded by a dense, obscuring fog of primordial gas. There is no light that reaches our telescopes from this time, which is appropriately called the cosmic dark ages. There is some background radiation from the Big Bang called the cosmic microwave background, a faint glow that shines to us from before the dark ages, but for the most part, the dark ages is a blank spot in our timeline of the universe. Astronomers hope the JWST will help them make sense of the end of the Dark Ages and figure out what caused this fog to lift, ushering in the cosmic dawn. Scientists suspect the starlight from the earliest galaxies did it. They reason that if you have a cloud of gas and it encounters energetic light, that vibrant light will ionize that gas and disassociate that cloud. And so if that light has just turned on, it then hits that gas and really transforms the entire universe from a dark place to a light place. Let's hear what you think of the JWST helping us to understand the Big Bang Theory better in the comments section.